Hi, my name is Kirk Weiler, and today we'll be talking about absolute maxima and minima in Math 4 Honors. In earlier lessons, we saw a theorem called the absolute maximum theorem, which said for all continuous functions on a closed interval, there exists some x value, we'll call it c, where the y value, f of c, is greater than or equal to the y values for all other y values in the interval. And likewise, there exists some x value, let's call it c again, where the y value is less than or equal to all other y values in the interval. Basically, this theorem just guarantees that there is a largest y value and a smallest y value, and further, x values that give us those. But we haven't been able to use techniques of calculus yet to help us find them. So let's start doing that in exercise number 1. It says, consider the function f of x equals x squared minus 8x plus 9 on the domain interval 0 to 7. It says find the location of the turning point of f and give all intervals over which f is increasing and over which f is decreasing. Alright, well, let's try to use calculus here. And what we're going to be doing is we're going to be finding the derivative, so go ahead and do that quickly. Alright, let's take a look. F prime of x is equal to 2x minus 8. If we want a turning point, at the turning point, the derivative will be equal to 0. And therefore, x will be equal to 4. If we want to now figure out all the intervals over which f is increasing and over which f is decreasing, we're going to draw our standard f prime number line. We're going to label our one and only one critical value. We'll take some values of x, like 5, and substitute them into the derivative, and we'll find that it's positive here. The derivative, that is, meaning that f is increasing. And if we took something like x equals 0 and substituted into the derivative, we'd find that the derivative is negative, and therefore the function is decreasing. Alright, so we can say that it's increasing over the interval 4 to infinity. Oh no, we don't want to say 4 to infinity. Just erase that a little bit. What we want to have is 4 to 7. Because we really have those endpoints on here. And that's really, really critical. So it's increasing from 4 to 7, and it's actually increasing at 7 because f prime is greater than 0. And it's going to be decreasing from 0 all the way up to 4, and that's because the derivative is less than 0. Now, it should be obvious then that what our graph looks like is something like this. We can tell that the minimum point is going to occur down here at 4. Of course, whether the maximum occurs at 0 or 7, that is still a large question mark. So let's take a look at letter B. In letter B, it says, determine the absolute maximum and absolute minimum values on the interval 0 to 7. Also, state where they occur. It may be helpful to sketch a picture of the function. Well, as we noted before, again, the function looks something like this. So the max has to occur either at the beginning of the interval or at the end of the interval, although we can definitely tell that the minimum occurs at x equals 4. The easiest way to simply do this is by figuring out the function's value at its two endpoints and at that one critical value. So we simply figure out what f of 0, f of 4, and f of 7 are. Remember, f of x is x squared minus 8x plus 9. Why don't we write that right here? X squared minus 8x plus 9. So f of 0, that's easy enough. That's 9. F of 4, all we would have to do is crank that into our graphing calculator or work it out by hand. But f of 4 is going to be negative 7. And f of 7 is going to be 2. So it's pretty clear that our maximum value is equal to 9 at x equals 0. And our minimum value is equal to 2. Nope, no. Our minimum value is equal to negative 7 at x equals 4. One of the main things to remember about absolute minimum and absolute maximum values is that they can only occur at two places. This is really, really important to know. They can either occur at a turning point, and that's a place, obviously, where the derivative is going to be equal to 0, or possibly undefined, or they can happen at the endpoints of the domain. Places where the derivative is equal to 0 and endpoints of the domain. So let's look at a slightly more challenging function. In exercise 2, we're asked to determine the absolute maximum and minimum values of a cubic on the interval negative 2 to 3. Alright, we know that they can occur only where the derivative is equal to 0 and at the endpoints. So the first thing that we're going to do is figure out where the derivative is equal to 0. Pause the video for a minute, take the derivative of your function, set it equal to 0, and solve for the zeros. Pause the video now. Okay, let's take a look at how this is done. The derivative is fairly straightforward. 3x squared minus 12x minus 15. We want to figure out where this is equal to 0. Might be easy if we divide both sides of the equation by 3 to get rid of that as a factor. X squared minus 4x minus 5 equals 0. Fairly easy to factor that. X minus 5 times x plus 1 equals 0. And so we've got our zeros at 5 and at negative 1. Now, a lot of students at this point start to kick into their relative minimum and maximum mode. They start drawing number lines and analyzing signs. But we don't need to do that. We know that the absolute maximum and minimum y values of this function on this interval can only occur at these x values or at these x values. So it's really simple. We're just going to go right on along. At x equals negative 2, we're going to figure out the y value. And of course, we're going to do that by just taking negative 2 and substituting into our function x to the third minus 6x squared minus 15x. Now, whether you're doing this on your calculator or in some other way, you're going to find y is equal to negative 2. And we're going to keep moving along. We don't really have to go in order, but I'm going to go in numerical order. At x equals negative 1, we'll put that into our calculator or into our function, and we'll find that the y value is 8. What's our next one? X is equal to 3. Our y value is equal to a whopping negative 72. And finally, our x value of 5 gives us a y value of negative 100. So this is our list. Or is it? A lot of students will look at this and they'll say, alright, the absolute maximum is y equals 8. And you know what? There's no question. That is the absolute maximum. It's the largest y value. But then a lot of people will look at this and say, the absolute minimum is negative 100. Think for a moment why that's not the case. Alright, hopefully you realize that this is not the absolute minimum because x equals 5 is not on our interval. That is a really, really crucial thing to realize. Right? All we're doing ultimately when we do a problem like this is we're saying as x goes from negative 2 to positive 3, What is the largest and smallest y value? Well, the largest y value that we hit was 8. But the smallest y value we hit was negative 72. And negative 100 is never hit because x equals 5 is not in the interval. Always keep your interval front and center. Let's take a look at the final exercise. This one combines a lot of what we've learned so far with derivatives into a rational function. The first thing they ask us to do in exercise 3 is find the derivative function. Pause the video and take a moment to do that. Alright, let's give it a try. I'm going to make my pencil thickness a little bit bigger now. We're going to find the derivative here using the quotient rule. Classic quotient rule. Quotient rule says find the derivative of the top, that's going to be 2x plus 1, times the denominator, x minus 1. And we have to subtract the derivative of the denominator, that one's easy, 1, times the numerator, x squared plus x plus 2. All divided by the denominator squared. Resist the urge to do something foolish algebraically, like canceling these x minus 1s. Can't happen. Also resist the urge to actually FOIL out or expand the denominator. There's really no need to do that. So what we're now going to do is we're going to simplify the numerator, but we're going to leave that denominator as x minus 1. Let's try that. Alright, so if we multiply out the numerator, we'll have 2x squared minus x minus 1 minus x squared minus x minus 2. And as I said, just leave the denominator as x minus 1 squared. Absolutely nothing else to do with it. Ultimately, what we'll end up having is x squared minus 2x minus 3 in the numerator, all divided by x minus 1, the quantity squared, in the denominator. Alright, let's get back to it. In letter B it says determine all critical values of f, i.e. values where f prime of x is equal to 0 and where f prime of x doesn't exist. Well, for f prime of x to be equal to 0, we know, because it's a fraction, that means that the numerator must be equal to 0. Of course, the denominator can't be equal to 0 at the same values of x, but we'll be able to tell that pretty quickly. So let's factor this. We'll get x minus 3, x plus 1, and x equals 3, and x equals negative 1. Neither one of those make the denominator 0, although when the denominator is 0, we get another critical value to consider, x equals 1, right? This actually is something that makes f prime non-existent. Does not exist. So we really have three values of x that we want to keep front and center. 3, negative 1, and 1. The next part of the problem asks us to find all intervals over which f is decreasing and increasing. You're probably getting kind of tired of this question by now, because it just entails drawing our number line of f prime of x. Let's get all our critical values on there. Let's get negative 1, let's get 1, let's get 3. Important not to forget that. We can now test a variety of values up here in the derivative. It again may be very helpful to think about our derivative in its factored form. Right? Its factored form would be x minus 3. I'm going to put it up here so we have a little more room. X plus 1 and x minus 1 squared. Boy, that just does not look like an x plus 1 up here, but maybe we'll erase that so it's a little more clear and get that x plus 1 in there. That's a little bit better. One of the great things about testing values in this derivative is that the denominator, notice, is always positive because it's a quantity squared. So for instance, let's take a number like x equals 4. If we put it in the numerator, it'll be a positive here, and a positive here, and a positive here. But we really only have to pay attention to the numerator. Product of two positives will give us a positive, so the function must be increasing. If I grab x equals 2, I'll get a negative and a positive, and again, the denominator being positive won't change anything. If I took our favorite like x equals 0, we would have a negative times a positive, which is a negative. Again, denominator is irrelevant because it's always positive. And finally, if I took negative 2, I would get a negative times a negative, and that would give me a positive. So I have a function that's increasing, decreasing, decreasing, increasing. Alright, so we could say something like this. The function is decreasing from negative 1, well, we could say all the way up to 3 actually, as long as we put something like this in, x not equaling 1. And then we could say that it's increasing from negative infinity all the way up to negative 1, union 3 to infinity. It's always important to explain why. Here it's increasing because f prime of x is greater than 0. Here because f prime is less than 0. It then says classify each point as the location of either a local maximum, a local minimum, or neither. Justify by using the sign analysis, and then it asks us for the y values of those local maxes and minimums, and adds in what seems strange about them. So we could add our typical explanation, i.e., x equals negative 1 is definitely the location of a relative max, right? And what's that line that we always say? Because f prime changes from positive to negative. We could say x equals 3 is the location of a relative min because f prime changes, we'll put it here, from negative to positive. They ask us for the y values at these two x values. That's easy enough to do. We can of course just take our x values and substitute them into our function, x squared plus x plus 2 over x minus 1. So x squared plus x minus 2 over x minus 1. If we substitute negative 1 into that function, we'll end up having 1 minus 1 minus 2. Let's just plug it right in. 1 minus 1 minus 2 all over negative 2. And that gives us a y value of 1. And then if we put 3 in there, we'll have 9 plus 3 minus 2 all over 2, which is 12 minus 2, 10, which is 5. So think about that for a minute. What seems strange to you about that? Does it not seem strange? Uh-oh, I've got some wrong y values here. Should have been a plus 2 there. Plus 2 there. Let's change that a little bit. We'll have negative 1 there, 12, 14, and a 7. What should seem strange to you is that we have a relative max here that has a lower value than this relative min. Now, normally, you don't expect that to happen. If you've got a relative max and you've got a relative min, it seems like that relative min should always have a lower value than that relative max. Let's take a look at what the absolute values are. Or actually, let's go back just for a second and explain that. What's going on here is if you actually look at the graph of this function, on your graphing calculator, let's say, it's got a vertical asymptote at x equals 1. And what's happening is we're getting a function that behaves something like this, where it's got a maximum that's actually less than the minimum that it's next to. Finally, let's do the absolute max and minimums values of the function over 2, 4. Well, remember, we know that those can only occur at x equals 2, x equals 4, or any critical values on that interval, the only one of which is x equals 3. So all we have to do in this problem now is take our function, x squared plus x plus 2, divided by x minus 1, and we just need to evaluate it for x equals 2, x equals 3, and x equals 4. At x equals 2, we'll have 4 plus 2 plus 2, all divided by 1, which is going to be 8. At x equals 3, we'll have 9 plus 3 plus 2, all over 2, which is going to be 7. And at x equals 4, we'll have 16 plus 4 plus 2, all divided by 3, 22 thirds, which is 7 1/3 for comparison purposes. So here we've got our absolute max, and here we've got our absolute min. Alright, that's it for this lesson. Until next time, keep thinking and keep asking questions, especially to yourself. Because as I always like to say, the more that you do that, the more you'll realize that you are your own best teacher. Take care for now.